All right, hello. I'm Brendan Mulcahy. Welcome to my talk. I'm a research engineer, and I'm the lead of the Learning Agents team. Daniel Holden and I co-created Learning Agents over the last year and a half or so. And today we're going to learn about Learning Agents. So here's what we're going to talk about today. We're going to talk about why. Why do we make Learning Agents? Why should you use it? How? How does it work? How did we use it in our Fortnite research project? And then what? What's coming in 5.5 and beyond? So if you're all here at Unreal Fest and you're an Unreal game developer, you know that we love video games. We love playing games. We love making games. We love everything about games, right? Well, maybe not everything. There are some things you probably don't like, and one thing that I particularly don't like is games that have cheating AI. So, I play a lot of competitive games, and I like to turn up the difficulty to the max, and I'm always disappointed when the AI is playing a sort of different game from the game that I'm playing. They either get extra gold, they get extra ammo, or they get extra sensory perception. But at the same time, I get it, because making intelligent AI is hard, and making it fun is even harder. So how are we going to solve this problem? Well, I think we can, but we can't get there with just classical game AI alone. What we need to do is we need more power. We need machine learning. And in particular, we need these two types of machine learning. We need reinforcement learning, and we need imitation learning. So I'm not going to cover all the details of these two things. You can go learn about that on your own online. But just really briefly to get us on the same page, hopefully. Reinforcement learning is similar to training a pet, right? You're going to give treats when good things are happening, or you're going to withhold the treats when bad things are happening. So we're going to put an agent in our game world. We're going to wire up the observations so that it knows, what's going on around it, how fast are objects moving, where are objects, et cetera. And then we're going to wire it up to the actions. So, it's going to be able to do stuff in the world. It's going to take random actions, and then we're going to write a reward function that is going to reward it for doing the behavior that we want it to learn to do. And as it randomly stumbles upon those rewards, it's going to get reinforced, and it's going to want to do that action more and more until it's no longer doing random actions. It's doing what we were trying to get it to do. So that's reinforcement learning in a nutshell. Imitation learning is a different take on that. So what we're going to do is we're going to have something else that we want to imitate, whether that be a player that is playing the game, potentially from replays, or we might have another AI system that we already have, like a behavior tree or a state machine, that can produce actions for us. And we want to create a data set of observations around that player or that other AI, and then we're going to record what actions it's taking and make this paired data set that we can then train our neural network on. So that's imitation learning. So why would you want to use these? Well, there's a ton of different use cases, and I'm sure you can think of more than what I have on here. But these are some things that I care about. So when I play games, I want to play against bots that are human-like, especially in Fortnite Battle Royale. When I run into bots and I'm playing a game, I can say, you don't feel like a player. So we can use imitation learning to create a data set to train the bot and get it acting in a much more human-like way, and make the experience of playing against the bots much closer to the experience of playing against players. So when we put new players against bots, we can transition them into playing against humans much easier. If we can get a big enough data set with tons of different examples of playing across the skill brackets, we can customize bot intelligence, where we can put in some sort of skill level or MMR, however you want to think about it, as part of the parameter into our model. And that'll allow us to have a much more tunable experience where we can deploy bots for new players or for veterans alike. And then finally, instead of having to reprogram our bots whenever new content comes out, if we're doing a live service game, we can maybe retrain instead. There's a new map. We don't have to reprogram the bots to handle all that new stuff. We can just retrain them and trade off programmer time for some computational resources. And perhaps that's a good trade for you. So machine learning is an extremely hyped up technology, and I think we all value skepticism as engineers. So I don't want you to get rid of all your skepticism, but at least for this talk, let's just put that aside and try to learn what we can. And I want to encourage, that I'm not telling you that machine learning is some golden hammer that's going to solve all your problems. This is just one more tool in your toolbox. So I want to say, everything you already know about AI, whether that be behavior trees, state machines, whatever, all of that is still really good and valuable, and we want to use that where it's appropriate. And then maybe we want to use machine learning in other places where it does its thing best. So just going off the battle royale, if we have wolves or we have frogs or whatever other creatures, those things are simple. It's way better to just go and program that using AI. But if we're trying to replace players in our lobbies, trying to program that and make it feel just like another human is extremely challenging. So that's where machine learning can come in. So let's use the right tool for the job. So we already covered sort of the first use case, which is I want to create AI opponents to play against that feel human-like, but also maybe I want to play against or have teammates that play in a human-like way who are bots. Perhaps that's something that could be valuable for you. Once we have bots that know how to play games, we can use them to automatically QA test. We can wire up our data instrumentation into our playtest server, gather a big data set, create a bot that plays like our QA testers. And now our QA testers maybe don't have to do so much golden path testing. They can go focus on the nitty-gritty bugs that are harder to find. And then finally, it enables us to do new sorts of games where we can be a teacher or a trainer, maybe like something like Nintendogs where you need to train a pet, and we can teach it and it can learn tricks in real time. Or maybe you're the coach of a basketball team and you're helping out your agents learn how to play basketball well. So that enables new types of gameplay, and definitely you can see emerging gameplay as part of that. So let's start to get into the technical details. So learning agents is an experimental plugin, and I want to just hammer that home that things are going to be changing. We're going to be updating it. We're going to be adding a lot. It's fully usable today. We shipped it in 5.3, so definitely check it out. The thing that's great for you is if you want to help contribute, you can use it, give me feedback, and we can make changes and try to make it the greatest machine learning plugin in the universe. So learning agents is for doing reinforcement and imitation learning, and has APIs for doing these things. So you can collect data, you can train your agents, and then finally, when you want to ship your game, you can run them directly with learning agents. So when we set out to design learning agents, we wanted it to be flexible and powerful enough for technical users to be able to customize and build upon. Devs who know C++, know Python, they're not going to be having to come ask us to add features to learning agents all the time, because we designed it in a way where they can go add those customizations themselves. But we also wanted it to be accessible to the non-technical users, people who love blueprints. We have the API fully supported in blueprints, and you can do all of your training directly in the editor. So you don't need to set up some complicated infrastructure. And then finally, as I mentioned earlier, we wanted to integrate really easily with existing AI technology. So you have a behavior tree, you want to just replace one node in that tree with a neural network, you can do that. You don't have to throw away everything and try to train your agents entirely from scratch. So sort of the flip side, some non-goals we had was we didn't want to make learning agents into a framework, because with a framework, we're sort of telling you that we know exactly how you need to solve this problem. And instead, we made it much more like a library where you use it to solve the problems that you care about, and even problems that I hadn't anticipated when we were designing learning agents. And then finally, since we wanted to create agents that are either going to run on a game server for a multiplayer game or run on an end user device for a single player game, we avoided including black box learning, such as using pixels as observations. We'll probably add that stuff back in later, but in order to steer people away from that and steer them towards using direct game properties so that you can actually get something that's going to run in your game. So for technical details, we use PyTorch. So when you're running your UE game process and you want to train, we'll spawn a Python sub process, and that's using PyTorch for training. You can do that directly in the editor, or you can cook your game and run a headless build if you need to get data collecting faster. And then when you go to ship, we fully support the neural network engine that comes with UE. And we implemented a custom backend for it called the Runtime Basic CPU, which can be used for fast cross-platform CPU inference. So if you want to run a neural network on a Nintendo Switch or on any of the mobile platforms or on a Linux server, whatever, learning agents should work for you there. So at a really high view, what does the code look like? So learning agents is built around this manager component, which you're going to drop in your scene, and then you need to register what are the agents. We're going to go through this car example where we're going to train cars to race around a track. So we'll be calling add agents to get agent IDs assigned to each of our cars. The manager's second responsibility is it keeps track of the actual program you're running, whether you're doing training or you're doing inference. And that's going to be supported by these manager objects. So this part is a little bit more of a framework where we try to help you design your program, but then you compose it yourself in the manager, and that gives you a lot of that flexibility I talked about. So we're not going to go into each of these components in extreme detail, but we're going to look a little bit more at the interactor in a bit. But you can see how these would fit into the different paradigms we talked about, whether it's reinforcement or imitation learning. So with reinforcement learning, you're going to use the interactor and the policy, and those are how you're going to hook it up to your game to gather those observations and actions. And then when you want to do your reward function, you're going to define that in a training environment. And then finally, you're going to add a PPO trainer, and that's going to be the actual algorithm that's going to train your agent. So if you don't know what PPO is, don't worry. It's still pretty easy to use. With imitation learning, you can reuse the interactor and the policy you defined, and then you're going to use a couple other components. So we have a recorder, which is going to grab those observations and actions and create that data you need to train. And when you want to figure out, like, are we going to be copying a player or copying some other AI, you implement that in a controller and implement the gather actions function. So that's how you can create that paired data set of states and actions. When we go to create the manager, it's just simply an actor component, and you can add it to any actor in your scene. And then we can call that add agents function that I talked about. So I'm going to show most of the demonstrations in blueprints. Everything is fully supported in C++, but I think looking at blueprints is more appealing in a presentation than looking at C++ code. So don't be alarmed that there's only blueprints, but the C++ API is great as well. When you want to go add manager objects, you're going to call these make functions. So we got make interactor, make critic, make policy, et cetera. You call those, you wire up the different settings, and then you can customize learning agents to your game. When you want to run training and inference, you can call this high-level function on the PPO trainer that'll run training for you. This is where a lot of the flexibility comes in, because you can wire that up wherever you want. If your game is like a real-time game and you're ticking, you can tick every frame of your game. You could also just adjust the tick rate of this actor, so it's only ticking maybe 5 hertz or something if that's appropriate for your game. And then if you have a turn-based game, and maybe you want to have an event where it's like the AI turn start, you can call run inference from that AI turn start. You don't have to call it from tick. So this gives you a lot of flexibility to run the neural network where you want to run it. When you're setting up the interactor, you're basically just going to override some functions. So you're going to specify observations and actions. That's sort of where you define a schema. And then in gather agent observation and perform agent action, that's where you're going to wire in the actual data that fits into that schema. We're going to look more at that in a second. And then you can see there's a similar thing with the training environment. You just override some functions. So now let's get into the really nitty-gritty details. How are we going to get the data out of our game, and how are we going to push the actions back into our game? So with 5.4, we wanted to make that easier, and we designed this feature we call structured observations and actions. So we were motivated by this question, which is how can we make it easy for game devs to specify what an agent observes and what its actions are? And I want to give you a kind of concrete example that hopefully you can wrap your head around. So let's say we're programming Jonesy bot here, and we need to wire up his observations. He needs to look at a lot of different objects in his scene in order to play in an intelligent way. He needs to look at trees, which are pretty boring. They just have a position and maybe a rotation. Treasure chests maybe have like an open and closed state. The guns have an ammo count. And then we have way complicated things like other players like Jonesy. So we need to gather different properties for all these different objects, and we need to somehow get that into our neural network. So that seems like an interesting challenge. With actions, we might have different paths that we need to go down. So some situations we want to move, in which case we're going to need to have our neural network output a direction and a speed. If we're trying to shoot, we might have a list of targets we can shoot at, and the neural network will output like a one-hot encoding of which target to shoot at. So what we're going to do is we're going to define sort of schema that maps onto this data. And then at runtime, you're going to write code that's going to provide the observation. And then learning agents will validate that observation against the schema. And then under the hood, learning agents will generate a neural network for you that has the appropriate architecture based on the data that you defined in your schema. So we want to encourage you to spend a lot more time thinking about your data than worrying so much about the details of the neural network. So here's what that might look like in a blueprint. When we want to define the schema for our observation, you're going to do what we call specifying. And you kind of read these from right to left. So we're going to take in a set of observations where each observation is made up of a location, an enum value that maybe says if it's a chest or a tree or a player. And then you can have optional observations. So maybe for the gun, we need to know the ammo count, and we can specify that we're going to have this thing that we might sometimes have. And then here's the one C++ thing I put here, because look at how beautiful it is to define that schema in C++. Then when you want to go gather observations, you need to actually get the data from someplace, and you're going to be calling normal functions that you're all familiar with. So here we're going to create a set of observations where the only element of that set is made up of an object that has a relativized location. It's got the type of the object, and then it's either going to give us the ammo count if it's a gun, or it's going to provide a null observation if it's not valid because it's not a gun. And you can see that we're calling functions that you know, like get actor location, get actor velocity, whatever. So we don't have like a whole new system for talking to actors in the game. We just create these slots, and you stick the data in as you need. On the action side, it's pretty similar. Here we define that an action is made up of either that choice between what target to shoot at, or moving, in which we need to have that direction and the speed. And then when we want to perform the actions, we're going to pull them out of the result from the neural network and then distribute them along. So we can have a switch where it says, if the action is moving, then we're going to get a direction of speed and then apply it to the move function on our actor. Or if we're shooting, we can pull out which target it was and then call the shoot function on our actor. So a lot of that was probably hard to understand in the moment. And if you want to take more time, I highly encourage you to go check out the course that we put together. It's available on the developer community site. And if you just search for Unreal Learning Agents, Learn to Drive, you can find it. And we'll go into a lot more detail than what I'm able to cover right here. So here's what you'll be creating. So by the time you're done with the tutorial, you'll have trained a car to race around the vehicle template. And we didn't have to program this at all. It just learns how to drive, and it tries to drive as quickly as it can based on the reward function we defined. So we want to maximize velocity, and then we want to avoid driving off the track and crashing into walls and all that sort of stuff. So you can see that looks pretty good, and that's what you'll be doing there. And then this time, it's always good to stop and think about performance really quickly, because you're probably wondering, okay, is this going to be fast enough that it can actually work in my game? And the answer should be yes. If obviously you can design some sort of really huge observations, and maybe you could run into problems. But if you're being intelligent about what you're doing, you can get results like this. So with this driving example, we have the cars racing around the track. And for observations, we need to calculate the distance to the spline. And that takes 19 microseconds or whatever. But then actually running our neural network under the policy only takes 11 microseconds. So if you really think about it, it's only those 11 microseconds that are anything new. Because if you were writing your old-fashioned classical AI system, you're probably still doing something like that spline calculation. So that's kind of not something you have to think about. So we can get this to run really fast, and we can do this in real time, and it's not going to affect the frame rate of your game. And then as you may know, if you've tried this before, there's a lot of debugging you need to do. You need to debug your regular code, but you also need to debug your data when you're training to make sure that your agents are actually seeing the things that you wanted them to see in the world. So in the vehicle tutorial, we have the spline, and then we have a set of points along the spline to show the shape of the track. And you can kind of see here what that would look like for the agent. And you can imagine in your head, like if I had those points and I was driving along, like I could probably learn to do that. And then you look at the bugged version of this, and the points are all somewhere else, and you're like, yeah, no wonder they can't learn to drive. I made a mistake somewhere. So this is a powerful tool. Definitely check out the visual logger. Can help make debugging way easier. And that is covered in the tutorial. So then we want to look at a research project we did with learning agents in Fortnite. So this paper is human-like behavior in a third-person shooter with imitation learning. It was presented this summer at the IEEE Conference on Games by our intern, Alex Farhang. And we'll go into more details about how this works. So in Battle Royale, player bots should do these two things. One, they should prepare players to play against other players. So we want the bots to play in a human-like way so that there's not a stark transition of playing against bots, and then you play your first match against humans, and it's just like completely, you get destroyed because you weren't even ready to play the game, really. So if we had the ability to have our bots scale in difficulty up to the point where you're ready to play against players, that could really create a great experience for players. And then sort of along that line, we want the bots to be able to adjust their skill so that if we have veteran players coming back, we can put them with bots and give them a reasonable challenge that they're going to have fun with. So we're going to try to solve both of these problems with this paper. So if we look at the existing Fortnite bot AI, it's going to look somewhat bot-like. So let's take a look at that. So you can see Jonesy was going to pick a point, sort of intentionally missing you, and then he's going to jump around. And if you've played Battle Royale and you're faced Jonesy, where you'd be Emmy in this case in the background looking at Jonesy, it's pretty easy to tell that Jonesy's not another player. So how can we solve that? So what we wanted to do is we set up our own data gym. Basically, we made a level where it's like a 1v1 fight, and you're gonna you're gonna play as Emmy, and you're gonna be shooting at Jonesy, and he's gonna be fighting back against you, and you're gonna hopefully take him out. He'll respawn at some place, and it'll reset, and you can play for 20 minutes and collect a bunch of data. And we could put other people on our team, play through this, collect a data set of a bunch of different people, and we're gonna log that off into files. So we're going to collect those observations, collect the actions, and make a nice little data set there. And then we did offline training in Python. So we created a neural network, trained it up. Then we grabbed our network, brought it in to learning agents, dropped in the editor, and we're able to watch, how does that model play the game? Does it look like how a human plays it? And then furthermore, we can run the same data collection on that model in order to generate some stats, so that we can, quantitatively compare how a human plays with how our model plays. So anyway, that's how the data gym works. Here's how it works with learning agents. So we're going to have Emmy add herself as an agent to the manager, and then we're going to use those components we talked about earlier. So we create an interactor where we define the observations that we need to play Fortnite. So an offset vector to the opponent, Jonesy in this case. We had some versions with trees, so we might have locations of trees nearby. And then we have the actions of controlling the pitch and yaw of the gun, controlling crouching, jumping, the fire rate, looking down the sights, and moving around. So basically everything you could do for combat. And then we're going to run the recorder, grab all those observations, all those actions, create that data set. And we can drop those offline in just some files that we can read somewhere else. So we needed to pick a model that we wanted to train. And for this paper, we didn't want to have like a super, we didn't want to go through a ton of different models. We wanted to pick something powerful and just kind of iterate with that. And you'll see why we did that in a moment. So the model we chose is this causal transformer, which if you're familiar with LLMs, it works kind of similar to that. So we take states and actions, which are represented in these arrays of floats, and we basically embed them into tokens. And then we're going to feed a sequence of tokens representing different times, right? So we're going to have 60 frames of data, which is about 2 seconds of gameplay. And then we're going to feed that into the model every frame. And then the model is predicting the action for every single one of those time steps. And we can train it by comparing the action that the player took to the action the model predicted. And that's how we're going to train this. So when we're doing inference, we train this outside of the editor in Python. And we output our model into the Onyx format, which you're maybe familiar with. That is fully supported in the neural network engine. So we can just take our Onyx model, drop it on the editor, do a little bit of some programming, since learning agents out of the box doesn't let you run Onyx models, but it's only a few lines of C++. You can wire it up. I'll get that added in there eventually, so you won't have to do that. And then we can run our policy, and then take that existing interactor we use to gather the data and just reuse that component when we're doing inference. So here's what our result looks like. You can see that Emmy knows how to move around, knows how to control the gun, knows how to do the triggering. And then the way it moves around in the space looks a lot more human-like. It misses very naturally, and it is able to shoot pretty well. So that was our first result. And then, like I mentioned, we can do some sort of quantitative analysis by basically running the model in the same data gym, and then we can take those results and compare them offline. So here's some stats we took. So in the orange, you could see if you had 2 of the AI bots fighting against each other, they end up with a 50% win rate, which is totally expected. Humans are quite a bit better than the bots, so you can see that they have a really high win rate. And then you can see that the neural network we trained is able to achieve a higher win rate than random. And you can see that that sort of trend continues with kills, accuracy, et cetera. But those high-level stats don't really tell a full story of, is it human-like? It just tells you, okay, it's better. So we need to look a little bit closer, and you can look here on the bottom and see that when you're acquiring a target, so that's when you're doing this big movement from, like, I'm looking over here and I'm trying to shoot somebody over here. I'm going to do this big movement, and you can see the yaw error changes like 100 degrees there. You can see that the bot does it in such a way that it's jumping around a lot more, and the human and the neural network are varying their movement in a much smoother way. And that's what gives it that human-like appearance. When we're tracking a target, so that's when our crosshair has gotten close to the target, and we want to just keep on it while we're pulling the trigger. You can see the neural network and the bot have different behavior as well. The bot sort of jumps around and has this quick transition between things it's looking at, but the human and the neural network sort of smoothly move around the space. So we wanted to take this one step further, and we wanted to see what else could we do with this model, since it's pretty powerful. So if we split up our data into different groupings, we can train different ID tokens, and we can use those as a prompt to the model in order to allow it to have different behavior. So this sort of solves that problem of, I want to be able to have the ability to influence its skill. So what I could do here is I could group my data into a low skill group and a high skill group. And then I could also do something like this. I could split it up where every player is in their own group, and I can create an ID token that way. And then I'm going to learn this ID token to try to match the behavior of just that group. I'm going to feed that in sort of like a prompt in an LLM, and it's going to allow the transformer to know like which group it's trying to imitate. So you can see the top-bottom comparison here of the high skill versus the low skill model, and take a close look at this. So you can see the high skill model tends to not miss as much. It's going to get kills a lot faster. The low skill model is going to drift around the space more, and it's going to do that in a believable way. And it's going to take longer to get kills, which passes the sanity check of what we were trying to do. And then we wanted to look at our individual skill IDs and say, are we able to replicate individuals in our database? And it's a little bit hard to tell, like if you had data of me playing and someone with a similar skill level to me, you know, what makes it play like Brendan or what makes it play like them? It's hard to do that. You know, it's hard to tell what's different. So we looked at some high level things like how much is one player crouching versus another, and does the neural network reproduce that? So you can see on the left here that if we grab those high skill human data and then train a high skill neural network, they somewhat closely match each other. And then if we do the same with the low skill data, you see the neural network also decreases its skill. And then, like I was saying with the crouching and jumping, we can look at individual humans in this set and see if the network reproduces that. So you can see that for the human 1, they don't crouch very much. Their neural network doesn't crouch that much. With human 2, they crouch quite a bit more, and their neural network crouches a bit more. You can see it doesn't work 100% of the time. For some reason, this third individual, they crouch a medium amount, and their network didn't crouch at all. So it's not perfect, but this is interesting because it shows how we can create bots that have different personalities, and then every single bot that the players run into don't have to behave exactly the same. And I want to remind you that this is running entirely in the editor using the neural network inference engine and using Onyx. So there's no Python at this point in time. It's just basically pure C++, and you could ship that in your game. So here's some takeaways. Imitation learning works. You can create a real-time model. And one of the best things is you can do it with a really small data set. So we collected only 8 hours of data in order to train that model. So it's something that pretty much anyone could do. You could be an indie game dev studio. You don't have to have a Fortnite battle royale amount of data to do this. It's not some sort of like science fiction to you. It's something real. You could do this right now. And then we wanted to show with the ID prompting that you could get the neural network to do anything you want it to do, really, as long as you can group your data up. So if you can get a bunch of skill buckets, you can train a bunch of ID tokens and have that tunable model. Or if you want to have that personality, you could group your data up that way and be able to prompt your model like that. And you could do whatever you can think of. So I put those question marks there. It's like whatever you could think of, and you can group your data, you can probably get the model to reproduce that. So finally, what's going to be coming in 5.5 and beyond? So a big feature we've been working on is re-architecting the training code. Going to look at that more in a moment. We've added more network protocols. I've added this thing I'm calling bring your own algorithm. For those who are more ML researcher inclined, you can add in things beyond PPO. And then finally, we got Mac and Linux training working. So for the training re-architected, it's a little bit small, but basically we used to have this huge make trainer block, and it didn't really have a lot of customizability to it. We broke that up. So now you got your training environment where you define your rewards and your completions. And then we have these functions like spawn the socket training process, make a socket communicator. Those allow you to control when that Python process is going to spawn under the hood. And then you call make PPO trainer. And you can see that that leads into the bring your own algorithm, because now you can call like make whatever your algorithm is trainer instead. For the networking protocols, previously we only supported shared memory, meaning you had to be training basically a Python process on the same machine as where the UE process was running. But we added the socket communicator so that you can have your UE process talking to a trainer that's running on a local area network. And then with bring your own algorithm, we added the ability in the settings where you can pass in the name of a file. So by default, you got your train PPO, which is going to run your PPO algorithm. But if you want to implement any of the other popular ML algorithms, you can do that in your project's content Python directory. You don't have to go modify the plugin anymore. And then finally, we got Mac and Linux training working. There's a bug on Mac with the shared memory. Turns out the engine doesn't actually have an implementation of shared memory. So we got a ticket filed for that. Hopefully we can get it done in the future. But you can at least train something using the sockets. And then finally, we got both of those things supported on Linux.
And it does work.
Oh, it works. So here's what's going to be coming in the future. We want to get training scale out. So currently, if you want to scale out your data collection for reinforcement learning, you have to have several gyms all existing in a single UE process. We're going to make it a lot easier for you to spawn a bunch of UE processes and be able to run those on virtual machines or containers. Or if you have a beefy workstation, you can spawn a bunch of UE headless processes and have them talking to a single Python trainer. So that's going to get your training results much faster. We've got a nice prototype of that worked out already. So instead of taking 2 hours to train the race car gym, you can get that down to 5 minutes. So that'll save you a lot of your real life wall time. We're going to work better on doing an editor integration. So having a custom toolbar where you can click and spawn these different scenarios of like how many training processes I want to have, how many data collection processes, et cetera. And then try to reduce our need to have TensorBoard. So maybe we'll have a nice GUI for you to look at there. And I want to remind you that these are things that we're currently thinking about, and there's no guarantee that these things are going to come. But I really want them for myself, so probably get them added in there. I want to take a look at imitation learning and get that all fixed up. Currently, when you're creating these data files, they're in a binary format. If you want to go read those in Python or some other language, you have to know the structure of that data. It's kind of annoying. So we're looking at maybe doing flat buffers. So you have the ability to generate your Python code for reading that data out. So that should be a huge usability improvement. And then we want to integrate that with the editor so it's easier for you to do your imitation training directly from the editor and not having to always click like run game and have that. So that experience should be a lot better. And then we've got various other features that we're constantly adding. So one I wanted to highlight is action masks. A lot of times in games, maybe you have a character that's able to shoot, and then they can get in a car and they're going to drive it. And they have actions like steering and pushing on the throttle and the brakes that aren't always valid, like when they're walking around in the world. So action masks are going to give you an easy way to tell that to your neural network. So it's only going to output actions that are valid for the current situation the agent's in. And then we're going to be doing a lot more stuff. So offline reinforcement learning I think is really cool. There's been some awesome papers on that. That's something I think we can get supported in the near future. And then just a quick call to action. If you thought any of this is really interesting, I highly recommend going to the course, going through it. It probably takes only about 2 hours of time to go through all of that. So that'll get you up to speed really quickly. And then if you have any questions beyond that, I'm happy to answer them at this point in time. Or you can catch me in the hallway or shoot me an email, whatever you want to do. So thanks for your time and attention, and I'll take questions.
Hi everyone, I'm Zoltan, and today I'm going to talk about how we expanded our traditional linear CG pipeline with real-time. So over this course, I'm going to go over different topics, such as how we integrated Unreal into our pipeline, what tools and what workflow do we use, and also I'm going to touch upon what projects we made with Unreal over the years. Also, I will give you an insight that how the whole transition went over within the company from different perspectives. And lastly, I will summarize that how much did we gain just by switching to Unreal. But first, a little bit about me. So I'm Zoltan. I'm an Unreal developer at Platige. And I have an ICT engineering background that specializes on real-time engines. And I was lucky enough to work with many different areas such as AR, VR, virtual production, and motion capture. But lately, I was more focused on tools and pipeline development. So that puts me around 8+ years with real-time engines and 5+ years with Unreal. But that's enough about me. Let's talk about Platige. So if you don't already know, Platige is an award-winning creative studio, and we have more than 25 years of experience with production and post-production. And we are currently operating with 5 different offices all over the world. We have also 6,000 projects with the most prominent clients, and we have been granted over 300 awards over the years. But pictures speak louder than words, so let me just show you what we have been doing.
Look what we can do. Ciao.
So I've seen this many times, but it still amazes me. So the first, I would like to talk about how we integrated Unreal into our ecosystem. So Platige was originally working with traditional linear CG pipeline, and that comes with some challenges. For example, the projects that we are working with are usually spanning between 3 to 9 months, and that puts a huge burden on the production and the creative work. The amount of iteration and creative work that can be done within this time period is quite limited. And also, every year, the clients are asking for higher resolution, frame rates, more content, and also possible sooner deliveries. And that restricts the amount of variety of the projects we can done. Also, if any last-minute changes are requested, it might be impossible to do so. The linear pipeline has the highest visual fidelity, but that comes with a huge demand on resources and time. The rendering times are usually taking very long to do. Therefore, they are introduced at the very late stage of the pipeline. And the final render can take up to 2 or 3 weeks to see. And therefore, it's really hard to iterate and do fast changes. Technological-wise, as we are doing tasks sequentially after each other, if something has to be changed, we have to go back several steps and do it all over. And if something goes wrong and it is very close to the end of the project, the artists have to fix it at post-production, which is really, really expensive. And so you can see this is quite problematic. We have some challenges to face. And you might have guessed what is the solution for this one. It is real-time, or more specifically, Unreal time. So Unreal proved over the years that it can create cinematic quality visuals for just a fraction of the time. It also introduced necessary tools for CG, like Sequencer, Movie Render Queue, OCIO, and many things more. And with the power of real time, we are able to see the almost final result in real life or real time. And it's really powerful because the artists are having instant feedback, and they can iterate much more faster. And with the gained time, they can be more creative in their work. It is relatively affordable, hardware and software-wise, and it has wide software integrations with other technologies such as Maya or Houdini. And as many of our artists have huge experiences in those softwares, it is really important for us. There are also many documentations and tutorials online, so if someone has to jump into Unreal, there is always something that they can just point to and then learn these things. Also, by switching from linear to real-time, we are switching how we are working. Now we are able to work parallel, and that really speeds up the processes. and also we are able to reduce the rendering time significantly. And if I mean significantly, it is really significant. Usually in linear, it takes 1 or 2 days to render out one shot. In real time, we are able to do the same thing in mere hours or minutes, depending on the complexity of the shot. On top of all this, there are a huge library of assets, pre-made assets, what you can choose from Unreal Marketplace, Quixel, or Megascans library, which is really amazing because many of the projects wouldn't be possible without them. Additionally, we have an amazing character creation pipeline in the form of MetaHuman, where we don't have to worry about character creation, rigging, sculpting, and animation. It is just out of the box, and it's really easy to use. Also, the projects are changing. We are able to deliver projects much faster or making them longer, depending on the requirements. And also, it introduces new business possibilities. And with the gain time, what we are saving on rendering times, now there is a possibility for episodic productions. And thanks that Unreal is used widely across the industry, now we are able to tighten the relationship with our clients. So now we know that Unreal is amazing. Now let's take a look at how we integrated it into our pipeline. The whole thing started at 2013 when the Infinite demo came out, and it showcased that now Unreal is ready to be used for cinematic purposes. And we started to look into it, how can we use it and experiment with it. And one example is the Another Day of Life. That was a project that we done in 2015, and it was done in linear. And we tried to recreate some of these shots within Unreal to see if it is able to do it. And it was very successful. And from there on, we tried to dig deeper and learn the tricks of Unreal. And we delivered our first project called Koala in 2020. It was just an internal project, but it proved that we are able to deliver a project from start till finish completely in Unreal. And we were really happy about it. After that, things got speeded up. Just a year after, we delivered our first ever client project, which was a virtual concert. And it was done within Unreal because there was a huge time constraint. And we weren't able to deliver it with other method. And we were really happy about it, and also the client was. And with the growing number of projects and demands, there was a need to also establish an Unreal pipeline that wasn't existing before. So in 2022, when us, the R&D team, took over the tools and pipeline development, it was essential to develop these things. And finally, in 2023, we received the Authorized Unreal Service Partner title. Now, as for the tools and workflow, in our work in the R&D team, our task was to create a new pipeline for Unreal. And we had to create a new pipeline for Unreal that would suffice the needs from artists till the management, and also would match the quality of the linear pipeline what we are having. So we had a lot of initial discussion with different departments, the pipeline team, to see what are the most core and essential parts of it. But luckily, we were able to narrow it down only to a few points. So first, the most important part is to import shots and assets in Unreal Engine. But that came with the need to create a unified project and shot structure. Secondly, we had to render out those shots and create movies automatically out of it, which can be later uploaded to ShotGrid for review purposes. Also, we couldn't just expect the artist to manually render out everything. Therefore, we added deadline support. And as some of the aspects were missing and functionalities were missing for the artist, we had to develop these tools, and we plan to use it via plugins. Of course, we had to version control the tool and the project, but we trusted Perforce and Git to do the rest of the magic. Lastly, the most crucial part, the engine itself. We decided to go with the vanilla version because we were a relatively small team, and also Unreal is way too robust. And the projects that we are working with are quite rapidly changing. We couldn't just stay and wait for 4 years, 5 years with the same engine version. However, we are still going with the custom fork of the Unreal Engine. You might ask why? And it's a very good reason behind it. So one of the days when I was sitting behind my desk, one of the artists wrote to me like, hey, the project what we are working on is crashing. And he sent me this picture. Have anyone seen something like this? All right. So for the developers, you might know it. What it means that all of our plugins, what we have in our project, is crashing. And this means that we have to make sure everything is working. And it's very hard. For the non-developers, it means that you're going to have a really, really bad time. So after some digging, we figured out that one of the artists downloaded the latest Unreal version from the Epic Launcher, installed it, opened up the project, but it was crashing because our plugins are containing C++. And we had to recompile it. Luckily, we were able to revert it back thanks to Paraforce, but that gave us a good sense that what artists should and shouldn't do. So we made what every sensible developer would do. We permitted them to submit changes to the plugins folder and the uproject file, so they cannot mess up the project in this case. And also, we permitted them to download the engines from the Epic installer. And we, of course, implemented our own way of downloading the proper engine versions. But it is really important to control what artists can do. As for the tools, I mentioned that we try to use plugins. And the reason why, because it is the designated way of propagating functionalities between projects. It can store assets, textures, widgets, many things more. And also, it is possible to enable and disable them per project basis on demand. Also, it is possible to, or they are separately handling the runtime and editor functionality. Our tools can be divided into two main categories. We have the core plugins that all the other tools are depending on, such as PI core, which is basically just containing all the packages and libraries that we are using. And the PI library, which is a function library that contains everything that the other tools are requiring, or some functions that are not exposed out of the box, or they just need it. The second one is the pipeline plugins. And those are behavior specific, which means that they contain everything to the role that they represent. So in this case, for example, in shot tools, they contain everything that is shot related. So shot creation, updates, modification, everything. And the same goes to the render tools. Contains everything that is render related. I mentioned before that we had to define a unified project and shot structure, and we decided to go with the level, sub-level, and sequence, subsequence setup, because that provides the most amount of flexibility for the artist to work freely. And of course, when we are working with this one, when we are editing something in Unreal, Paraforce will check out some assets, and that logs it. And it goes against the parallel workflow. But by dividing into smaller chunks, like additional sublevels, additional subsequences, we are able to maintain the parallel workflow and also the proper version controlling system. Here you can see that how our main sequence are set up. So we have a bunch of other subsequences with different categories. So we have the environment for all the environmental artists. We have the light for the lighting artists. And the same goes for the levels. We have one main persistent level, and all the sublevels are there. We also put some additional folders in the outliner for the artists to work with, so they can organize their work much better. So what we can see here, it is for word composition, but we also supporting word partition. Instead of sublevels, we are creating data layers with the same category names, so it should be covered everything. The first tool, what I'm going to showcase here, is the shot builder itself. This is how we are importing and creating shots. And it's a very simplistic way. It has just the shot names, the shot ranges, and the status what it has. And every data what you can see here is coming from ShotGrid. We just fetch it, and then we display it. We're able to select one or multiple ones. And in the bottom, we have additional subcategories that we can create on demand. Lastly, we have the two buttons to either import or update the shots. So when we import the shots, it will just iterate over the selection and create all the assets that I mentioned before, the sub-level subsequences. It will automatically open it up and update the status in the UI as well. You can see the levels are added automatically, and in the sequence, we have everything how it should be. There are two other unique assets what we are creating, called shot container and sequence container. but I will touch upon those just in a second. So these custom containers, we are using it for storing the information that is everything shot related or sequence related. And we are storing what we have from shot grid. So if there are any differences, like shot ranges or references, then we know it, and it will be displayed in the shot builder, in the UI, and then the artists are notified, and they can act upon it, they can update it. The second tools what I'm going to show is the render manager. This is our most used tool, and it's also very simplistic. So on the left side, we have all the available shots that are imported in the project. And on the right side, we have render options where we can select the primary configuration, either other options, if you want to create previews or upload them to ShotGrid, and also write some comments. Of course, the two buttons to either render it out in different ways. The second part of it is the render manager's assets. And what it does, that we have an asset folder into our structure, and it will iterate over and scan everything, regardless of the asset type. And it will just fill out the database, and we are using it for creating turntables. So when we are selecting it, it is not related to different sublevels, but we are using just for a studio setup to create turntables. And it's really useful for the artists and for the producers to asset and character creation. Now let's take a look at in action. So when we open up, we can see it's populated with the level, with the shots. And when we click on the level and the sequence, it will open up automatically the corresponding assets. Now we can change it to different configurations. Here I selected to have the create preview, upload to ShotGrid, and there's some just dummy text, what you can see. First, I'm going to demonstrate the local render itself. So when we push it, it's going to just open up the standard movie render queue, what we are using. But based on the selection, it will also export and generate a movie sequence out of it. And if you selected the ShotGrid, upload to ShotGrid, it will be also propagated up there. So it jumped into the export part, and just in a few seconds, and it's done. And now it is ready to be reviewed. So it's really easy for the artists and for the producers. They don't have to do these things manually. It's really amazing. The second part is the deadline render, or the remote render. And it has a very unique part of it where we can specify the render machines that we want to send it to. It's especially useful if you have a very heavy scene and you have a powerful machine that can handle it. You can just delegate it there. So what it does, it creates a job. It first ensures that the Unreal Engine is installed on the machine. If not, it's going to install it. Later, then it gets the latest version from Perforce of the project. And when it is done, it's going to also do the movie render queue. And based on the arguments, it's going to upload it to ShotGrid. So when we reload it, it's going to be there. So it's ready to be reviewed. It's really amazing, and the artists are really happy about it. And also we. As you can imagine, that we have a lot of projects and tools to maintain. Therefore, we try to automate as much as possible. So first thing what we did here is we created a GitLab CI that would get the latest version for all of our tools and make sure that everything is all right. And it will deploy to all the active projects what we have from ShotGrid. And then it will just submit it to Perforce. And it's really amazing because it eliminates the human error factor. And because we've done it before manually, but you always forget something or something goes wrong. And it's automated. It's really, really handy. So you see now the tools. Now let's take a look at some cool stuff, what we are doing with Unreal itself. So let me just show you. So in terms, for Platige, it was a huge risk to deciding to deliver projects using Unreal only. It was unheard at that time. We can call it a leap of faith. But thankfully, it was really successful. From 2020, we delivered over 30 projects, and every year the number is growing. As you can see, we worked with virtual production, commercials, shorts, game trailers, and many things more. And we try to not limit the use of Unreal only to a certain type. We are using it all over the company. Due to the sheer number of the projects and the types that we are using, I try to take a look at them one by one. And the first project, what I would like to talk about, is Little Ruby, one of our short films. Here you can see that it's very stylized. And we try to push the use of Unreal outside of the commercial use of hyper-realistic. So this is very cartoonish looking, and it's a very good reason why. And we try to combine the 3D with 2D. You can see we have a lot of matte paints, and the style, what we are having here, is very flat shaded. Also, we are animating in 2s, just to give another punch to it, but really, really happy about it. The unique part of this one as well, that we had to design the whole project and the assets from the very beginning in mind that is going to be cartoonish looking. There is no asset library where we can just pick down these assets. And we had to make sure it's going to look good. For example, in the bottom, you can see that if you just have the model itself and put it into Unreal, it's still not looking perfectly. We had to make it flat shaded to make it more believable. The second shorts, what we are having here, is the Happy Holiday and the Happy Easter. Both of them were internal projects, and the whole purpose was to give the artist take a little break from the client project and explore the freedom and the creativity what they have. And they were relatively short, like one month projects, but there were no supervision. They were responsible for the story, execution, the ideas, everything. And they were really, really amazed by how good Unreal is. Also, it made their relationship much tighter, so I definitely recommend to try it out. A unique part of the Happy Holiday, which is the top one, that just 2 days before the deadline, Vov, the artist, decided to, why not try to turn it into a game? And he just made it in 1 day. And that just proved over that what we can achieve with Unreal. We can easily jump between different solutions, even though we started with one idea. The second big category, what I would like to talk about, are the game trailers. And first of that one is the Stormgate. It's relatively new. And what is unique about this one, that this was the first project for us where we used custom metahumans. As you can see, these characters are very cartoonish looking with unique proportions, and they are not supported out of the box with the MetaHuman pipeline. We had the artist had to find external tools and plugins to make it work, and there was a lot of room for experimentation, but luckily we were able to do it. Also, most of the visual effects, like explosions, fires, and also the sphere, what you can see, is done within Unreal. Like we don't need any other external programs to do so. And it's really amazing because we are saving a bunch of time with that one. The second project here is the Warhaven. And we were lucky because the client what we have been working with are using Unreal Engine as well. And we were able to get a lot of props, assets, and characters as well from their engine and just import it and use it in our case. Of course, we had to touch upon that one. We had to improve it to bump up the quality for cinematic purposes, but we couldn't have done this one in the linear pipeline before. So it's another big plus for the Unreal. With the growing number of possibilities, we couldn't just stop to use it for CG and visual effects. We could use it for virtual production, broadcast, environments, and many things more. So here you can see in the top left, we created a virtual environment for Disney. We made virtual production for music videos for the effects, and also we are using it every day for broadcast solutions. The last type, what we have here are the commercials itself. So these commercials, First, we have the Lima virtual model. It's very unique because it was a long-time dream for Plattish to implement a virtual model which can be customized, animated for the fashion industry, but it was quite challenging and expensive to implement it before. But thanks to MetaHuman, now it was achievable. What you can see here that we made actual motion mockup session where we hired a real-time or real-life model. We recorded the movement and also the facial expressions with the head-mounted camera, and we imported those animations into Unreal. We rendered them out, and now it was ready to be used. And we are proud to say that the Lima virtual model had its first public experience at Vogue magazine, and it was widely successful. Here we have the 3D explore the possibilities. It was a showcase of Unreal, what it's capable of, and it was a big, long master shot. You can see that we have interiors, huge exteriors, flybys where we have dynamic lighting as well, and also we have very realistic and very stylized look. And just really, we wanted to showcase what Unreal is capable of. Lastly, we have the Aston Martin Vantage. And it was a quite unique project in the terms that, as you can see, the car was driving in a huge city that was made entirely out of marble and crystals. And so, which means there's a lot of reflection. So in order to tackle this problem, we had to wait a little bit for Unreal 5 to take advantage of nanite lumen work partition. But it was gracefully handled thanks to those technologies. And what you can see here as well, that every animation what we have here, the crystals are also done in Unreal. And it's really amazing to see that what you can achieve. Now for the transition itself, I would like to start with the management point. To incorporate and change this volume into an existing ecosystem, you can imagine that there should be a very good motive to do so. And the whole idea started at 2019 with a growing number of needs for new possible clients. We also hope to speed up some of the processes with Unreal or even replace them and reuse the enormous rendering times what we are having. The whole structural change started by creating a new dedicated branch within the company called Entertainment Team, and their sole purpose was to create Unreal projects and work with Unreal projects. Many of the colleagues, what we had there, were really looking forward and were actively pushing to use Unreal before the branch was created, and they were really happy about that they could finally work with that one. In the beginning, we had some initial challenges, because there was lack of basic tools for the management, like creating reviews, submitting, managing processes. And it was a huge investment in terms of money, time, and resources to create a new pipeline from the scratch up. Also, many people had to familiarize themselves with the new tools and learn the limitations. But when the pipeline started to develop and established, we introduced Unreal as a regular tool from the very early stages to the client. We had a bunch of internal trainings and workshops to teach people what is the new way of working and how to use our tools. And with that one, we were able to work more creatively in their everyday work, and we got instant feedback whenever we were working with clients. As for the projects, we got new project types, what I mentioned, like virtual production, virtual production, theme parks, in-game cinematics, and many more. And thanks that other people are also using Unreal, we are able to tighten the relationship with them. We were able to deliver content, much more content with significantly less people, and we could do much more faster iterations in the project. Now, as for the artists, they had also a bit of bumpy start. There were no unified project structure in the beginning. So if one artist had to jump from one project to another, they were really hard to navigate and orientate themselves. There was different folder names, different level names. It was a bit chaos. And also there were lack of basic tools. They had to perform the importing shots, creating shots, assets manually. And it didn't help the situation that not many people had prior experience with Unreal itself. But I promise it wasn't all bad. it got better. So when we, the R&D team, took over, we immediately unified the project structure. We automated most of the steps. We provided them with the core tools, what you've seen, the show tools and the render tools. So with that one, they could develop project much more rapidly. They could integrate Unreal from a very early stage for shot framing, block out, previews, and many things. And the experienced colleagues started to share knowledge between each other and also with the new guys, so it was much better. Right now, we have a very efficient pipeline where most of the time, or almost everything is automated. We have even specialized tools for the artists, such as automatic landscape material, splines, roads, which is spline-based, or PCG tools. And we have a bunch of documentations and tutorials for them to learn if they don't know what to do. As for the developers, we had in the initial part, we had to understand what are the requirements and what do we have to do. So first, we take a look at what we had in the existing pipeline, and then we determined the core points, and then we had the initial planning. So in the first stage, we developed those core tools. We automated all the manual steps, what we were having in the artist's work. And after that, we could focus on the new features. So Unreal always releasing amazing tools. Now we could take a look at what can be used in the later stage in other projects. Also what our artists have been cooking, we can just reuse it and turn it into plugins. And in the last stage, of course, we can create documentation and tutorials. So whenever something goes wrong, we can just point that to the artist, and then they can just go over that one. Some words to live by. We use plugins for our tools. We use widgets for the UI. We use Python for interoperability because we have many different systems that we have to communicate: deadline, shot grid, Paraforce, things more. As for the functionalities, everything that is going in engine, we are using blueprints and C++ because it is just way too powerful and it's really amazing. And then, yeah, we develop the core tools and we try to turn good features into plugins. As developers, you're going to work with both artists and the management. And here are some tips that what we learned is a good point to learn. So for the artists, try to show them the benefits and the limitations of the engine itself. There are key differences how we're working with the linear pipeline in real time. And when they know it, it's going to be much better in the long run. Also, try to show them the credible sources, because you are not going to be always there, and there is way too much topic to cover. But if you show them where they can find the proper answer, it's going to be much easier. Also, try to build trust by support. So be ready that they're going to come to you and ask the same question over and over and over again. How to get the latest version of Paraforce? How can I create shots? That's completely fine, because just imagine like they have been dropped in a whole new world and you are the only point that they can turn to. But I recommend to support them as much as possible. And also be ready that you're going to be a jack of all trades. You will learn how to create tricks, how to animate, how to make visual effects, because the artists will come to you and expect answers. And in order to properly answer the questions, you have to learn all those things. But for me, that's part of the joy of the job. As for the management, try to convince them to start small with an internal project, because there you don't have any pressure from the deadline and from the clients. There are a lot of room for experimentation and for the creative work. If it is not possible, try to be part of the project planning from the very beginning. They will eventually learn what they can do and cannot do with Unreal, but in the beginning it's good to have you there. As for the tool requirements, try to get clear requirements from the very beginning. You will thank it for the long run. As for the pros and cons, everybody said like real-time rendering is amazing. The reuse rendering times is even more amazing. We are able to work much more faster. We are more flexible at the final crucial stage of the project. Like before that, everybody was afraid that, oh, we have the final delivery in 1 week, 2 weeks, going crazy. Now we are able to change things in the very last minute, and still we don't have to worry about it. We have amazing tools with Unreal, and there are also new project types, what I mentioned before. As for the cons, what we experienced that it's hard to find experienced people that have a knowledge both CG and Unreal. And also there's a steep learning curve because many of the systems what Unreal uses have like so many things and so much depth that you have to have prior knowledge to it. For example, Niagara, you can really create easy stuff, but in order to create amazing and complicated stuff, you really have to deep dive into it. Also, people tend to develop huge expectations towards Unreal. They treat it like a silver bullet, like you just throw things at it and it's going to solve everything for you. No, you have to somehow manage it. Like it's really amazing, but you have to learn how to work with it. Also, we have to rearrange the production steps, and we expect that the file size can grow really, really huge. Now, as for the tips, try to lose old habits as much as possible from linear pipeline. It's such a game changer that you can't really transfer most of the stuff from linear to real time. And that comes to the next point, that do not fear the unknowns. I know it's crazy and fearful to jump into a new world, but we had just positive experiences by introducing Unreal. You could be more open to the client's expectations. With this freedom, with the creativity, you can be more playful during the project. Also, start small, build on top of it if possible. Optimize as much as possible as well. Like in the linear pipeline, you don't have to worry about it. You can just brute force everything there. But here, in order to get the most out of Unreal, you have to take care of these things as well. Learn the limits, watch a lot of tutorials, and we can summarize that it's easy to play but hard to master. Now as for the conclusion itself, here are some interesting statistics. So with the automated shot and asset import, we're able to save 6 to 18 man days per month, and with the asset validation, 8 to 26 man days per month. It's really amazing because it was done manually beforehand, and now we can just use those manpower in somewhere else. But what is really interesting is the rendering times. So in linear CG, to render out one frame, just one frame, it can take up to 2 or 4 hours. In Unreal, we can do it in mere minutes or seconds. And that really shook the foundation how we are approaching problems, because we don't have to render that much about rendering times. We can polish the projects. We can finalize it as much as possible. Also, we get new project types. We have in-game cinematics, thanks to we are sharing the same game engine. We have VR projects, virtual production, and also theme park solutions. We have also now 15% of the total revenue that comes from Unreal. And it's quite surprising that we have been working approximately 5 years, like very seriously with Unreal, and now it is 15% total. Another thing that in 2023, we delivered 4 times more projects just the year before. And this number is just growing. What we can see on the market, that the demand is growing, and also the clients are asking just to use Unreal. So in total, we finished over 30 projects in 2020. And we are proud to say for our achievements that we got the title of Authorized Service Partner. And 2 of our short films actually won the Best Short Animated. Little Ruby got the Chicago Film Festival and the NAACP Image Awards. And the Happy Easter got the Australian Effects and Animation Festival. So thank you very much for your attention, and hope you liked it.
Hi everybody, my name is Louis Tremblay and we are here to talk about the physical character controller that we developed for our game Eternal Strands. First, I will cover who we are and who I am and give a short intro of the game. Then, I will explain what we mean by physical character controller and answer why do we want to have one? Why do we want that complexity? Next, I'll go over an overview of the implementation, followed by a deeper dive into two use cases, walking and climbing. Lastly, I'll briefly go over how we approach animation of the main character. Yellow Brick Games is a small studio started by AAA veterans. The studio was founded in Quebec City in 2020. We started with less than 10 people, and we are now over 65. Although we are a small team, what I'm about to show was not done by a single person, so here are the members of the team involved with the physical character controller. As I'm standing in front of you, here's a little bit about me. I'm a programmer with more than 20 years of experience, with 18 years spent at Ubisoft. I worked on numerous Assassin's Creed games, 2 Splinter Cell, and a few other titles. I joined Yellow Brick Games as the first programmer a few months after the studio was founded. Since Eternal Strands is not out yet, most of you will be unfamiliar with it, so I think a short introduction would be welcome. Eternal Strands is a third-person fantasy action-adventure game. It's a single-player game with a strong emphasis on fighting and climbing giant epic creatures. We are inspired by games like Shadows of the Colossus, Dragon's Dogma, and Zelda Breath of the Wild. Let's have a brief look. Thank you. With the intro behind us, let's talk a bit why we would like to have a physical character controller. First, what do we mean by that? In a lot of games, the main character is moved entirely through kinematic movement. It's a fancy way of saying that the main character is essentially teleported where it needs to go. If there are some objects overlapping, the character overlapping at the destination, the objects will be simply pushed away. This is fine for a lot of games, and there's nothing wrong with that approach. It's limited, though, when you want the character's movement to be more physically accurate, like being slowed down when pushing on objects. It's the same problem when you want to be pushed around by heavy objects hitting the character. A physical character controller allows you to see the character as a physical particle. It gives it inertia and let the character behave as any other physical object. With that said, we are still making a game, so we are not aiming toward perfect realism. Why we would want that? We wanted our movement and climbing mechanics to not be animation-driven, like in a typical kinematic approach. Since we wanted the player to behave realistically around moving objects, we did not want the animation to be the source of movement. Instead, we wanted the animation to follow the character's movement. Since we are making an action-adventure game, we wanted to have an environment that was as dynamic as possible with a lot of moving objects. We wanted to let the player experiment with physics without a lot of restrictions. That means that a lot of unforeseen interaction could happen. Because we wanted our team size to be a lot smaller than typical AAA projects, we could not rely on a big animation team, and this has the direct impact that we were unable to produce a lot of animation to cover all cases. with a very dynamic environment, it would have been difficult to have strict metrics for our systems. So we opted to not have any, but we still need a system that can handle any in-game situations. On top of having a dynamic environment, we wanted to allow the player to climb everything. This includes the static environment, of course, but also very big epic creatures. We wanted the player to have total freedom on where they can be on our epic. That means that we do not want to only be able to climb on very specific points, or in the same way, we do not want the player to be only able to transit from one specific point to another. We also want to have a limited amount of destruction in the game. Objects can disappear when the player is standing on them or move while they are climbing on them. Here's an example where one of our enemies is cutting down the tree the player is climbing on. Moreover, we wanted the character's movement to feel as physically real as possible. Even if a lot of players would not understand the underlying system, it just feels right. We wanted more than simply apply a force to our character to push it around. Just doing that is like having a small rocket in our back. It would move us using physics, but it will not be sufficient to replicate how a character walks. We wanted her to push on objects to move forward. That way, a character standing on objects would move them when walking on top of them. For the same reasons, we wanted to pull on objects to climb. Put in physics terms, we wanted to follow Newton's third law of action and reaction. These two examples will show what I mean. As you can see, the springboard goes downward when our character jumps, while the others show the box moves when we stop abruptly on them. Lastly, as the whole thing is in place, it would hopefully solve a very complex situation for us without additional work. To give you a concrete example of the kind of interaction we wanted to achieve, here's an example in our game. In this video, you will see our main character, Bryn, use two of her powers. The first one lets her build arbitrary shapes of ice, while the other can grasp parts of it and throw them by telekinesis. This showed that we support climbing on arbitrary geometry and fall when our supporting platforms fails us. It's time to go a bit over an overview of our system. Let's start with the basics. Again, we are a small team, so we do not have the programming resources available in a typical AAA project. This leads us to integrate as much as possible with the existing Unreal Engine code and avoid complex merge when integrating newer version of the engine. We started the project using Unreal 4.26 and physics. We are now using Unreal 5.3.2 and Chaos. We did not upgrade to 5.4 because we are near the end of the projects and we do not want to create new issues. We did, however, integrate changes from 5.4 for bug fixes and optimization. We also integrated most of the changes to Chaos submitted after 5.3. Our own engine's modifications are related to exposing functionalities and tweaks systems for needs. With that said, our character controller code is in a subclass of the character movement component. We did subclass other classes, like the player controller, but almost all the code for the character controller is inside our own component. Like Unreal's default character movement component, we are still using capsules for collision, and we are making sure it always stays vertical when walking, running, and falling. It's not true when climbing or sliding. In these cases, the capsule can be in any orientations. Character size does not matter. Also, epic creatures are not a special case for our system, and we are using it. Like I said previously, we do not want to apply forces directly on each character's capsules. It will not make objects we are standing on react properly. Perhaps we could apply a force on each other objects that we want to push or pull, but Chaos, like other physics engines, offer a better way, constraints. So for moving our character's capsule around, we are exclusively using constraints. A constraint lets us express a physical relationship between objects and gives us a way to have proper interactions between them. We did not write our own custom constraints. Although it's certainly possible to do so, we only use the constraint present in the engine. This ended up being a very good decision when we migrated to physics, from physics to Chaos. We did not have to touch anything. Before going further, some of you might need a refresher on what a constraint is. For this presentation, it's important to have a basic understanding of them, so I will take a few moments to explain what they are. This will not be exhaustive nor completely accurate, but good enough to give you an understanding of them. At its core, a constraint describes a relationship between two objects. This relationship can be a location relationship in 3D space. For example, I can describe that I want 2 points, each of them on the surface of two objects, to pull toward each other so that both points overlap in space. With this relationship, both objects will move toward each other, a bit like this. They might also change their orientation to accommodate the relationship. Since constraints take mass and inertia into account, the amount of translation or rotation will differ between the two objects. In the same manner, a constraint can describe a velocity relationship. I can describe that I want one object having a certain velocity compared to another. The relative part here is important. The relative velocity of a character walking on the ground is the same as the relative velocity of the same character walking on the back of a flying dragon. You can use a constraint to specify both relationships at the same time, asking an object to be at a specific place and at a specific velocity relative to another. The constraint will try its best to respect both relationships, but it might not be possible due to depending on the in-game relationship of the two objects. If you want to have a relationship more important than the other, you can do so with the constraints configuration. Once you have created a constraint, the solver will then try to generate forces on both bodies to fulfill what you asked. The generated force will be equal in magnitude, but opposite in direction as Newton's third law. Basically, to walk forward, our character will be pushing the ground. The force is equal to delta position times spring plus delta velocity times damping. This is not as scary as it seems. Delta position is the difference between the current position of an object and where you want it to be, while delta velocity is the difference between the current velocity and what you want it to be. Both deltas are expressed relative to the second objects in the relationship. In my previous example of a character walking on a dragon, both deltas are relative to the dragon. Spring and damping are, in this case, expressing how strongly we want to reduce the associated delta. Note that spring and damping are not scalar values, but vectors, so we can modulate how a constraint is applied on the axis of the constraint. For example, we can prioritize solving location on a plane while prioritizing velocity on the normal of the plane. Here's a few other notes. We never use linear or angular limit. We always configure our constraint to have 6 degrees of freedom. This means that constraints are not limited in any axis of movement or can rotate in any direction. As they express our character's movement, we do not want to have any restrictions. We are always using linear and angular drives. And we vary the spring and damping quite a bit based on the context, so we can emphasize on location versus velocity as needed. To do so, we typically have a 10+1 ratio between spring and damping to express the priority. Lastly, and it's very important for our character controller, we always have a force limit. That way, we can abstract a grip and express our character's strength. The greater the force limit, the easier it is for the character to resist changes in velocity or position by external forces. It also means that a character will be able to accelerate faster if needed. It's a parameter that we manipulate a lot based on the context of the character. With all of those boring stuff, it's time to look a bit at our first implementation case. So I will begin by the simplest one, standing still, then I will look a bit at walking. The simplest state that we can be is standing still on the ground. Standing still on a moving platform is conceptually the same. We want to stay on the same location compared to it. So when standing still over a moving platform, our speed in the world can be non-zero. Relative to the superlating platform, though, it is 0. In this example, you can see Bryn following a platform that is moving and rotating in space. The surface normal is shown in cyan, and the small white circle between her feet is the constraint location. Conceptually, we want our constraint to express a location relationship with a high priority. We care a lot about our relative position compared to the platform. We care less about velocity. This is because we want to follow our platform, even if it changes velocity or changes its direction of movement. To achieve this, we configure the constraint to drive location on all the constraint axes. Since we want to prioritize location, spring values are much higher than damping. And we want also our character to stay vertical, so we configure the constraint to maintain the orientation using angular velocity drive. When walking, we want to move relative to something else, so this adds a layer of complexity. Moving implies deciding where to go, so let's look at how we do this. The first thing we do is to consider the player's input. It informs us in which direction the player wants to move. With it and the current character velocity, we compute our target velocity. As I mentioned before, the target velocity is relative to the supporting platform. This is important because we do not care about world space velocity at all. To obtain our target transform, we do a straight application of Newton's kinematic movement equation, so there is nothing surprising there. In this example, you can see our target transform in blue and the current transform in red. At this point, we need to adjust the target transform to consider the objects in the world. We adjust the location by sensing the world with multiple sweep tests. We sense the world in the direction of the velocity and downwards to find any blocking collision and adjust if needed. This gives us a final target in space that can contain our character. Here, you can see some of the sweep tests we perform in yellow and the target transform in blue. When we are sweeping the world, we do not directly sweep from the character's current location because this allows us to ignore small bumps in the geometry and let our system easily go over them. Following the ground is delegated to the constraint, as you will see in a moment. Notice that in my example that the target transform is adjusted in advance when reaching a small bump. And we do that every physics update, not at every frame. The way we configure our constraint is different than when standing still. Here, we can see Bryn walking around on a platform. The red capsule shows where she is located, while the blue capsule shows the location of the target transform. At the bottom of both capsules, using white circles, you can see the two different positions of the constraints. One for where we are and the other where we want to be. For movement, we prefer to prioritize velocity. Since the player wants to move, we care less about its exact location. This is different than standing still, and it is important. For example, if we are pushed away by some external force while walking, prioritizing location will work against us as it will try to bring us back to a specific location on our platform. Driving velocity We'll instead try to maintain our velocity, but will allow some level of displacement by the external force. We align the z-axis of the constraint with our platform surface normal, and we drive velocity on the xy plane of the constraint. Although we want to prioritize velocity on the surface of the platform, we prioritize location on the z-axis of the constraint. This allows us to stick to the supporting platform and avoids launching the character up in the air when he reaches the end of a small slope. If we encounter small bumps in the geometry, the capsule will simply slide up and follow the ground. Like when we are standing still, we maintain the orientation using velocity drive. With walking explained, let's look at the result. We can now take a look at climbing. It's a bit more complex, and both in concept and implementation. The first key difference between walking and climbing is that we want to allow the character to have multiple supporting platforms. It's needed, for example, to properly support climbing on our epic creatures. The character could have both feet and hands on different body parts. We also want to support having one or more of the platform to become invalid, either by moving away or simply being destroyed. This cannot be expressed with a single constraint, so we use 4, one for each limb. Here, you can see Bryn climbing on a wall. A lot is happening, so let me take a few moments to describe what you see. Each white circle shows where a constraint is located on the wall. While the character is moving, you can see that each limb tries to reach for single constraints. Once a limb reaches the constraint location, it becomes locked in place and stops moving. At some point, if the character continues to move, the location of a limb will need to be moved simply because of the character's morphology. At that point, we move the constraint to a new position and the cycle begins anew. Since we have 4 constraints, the character's capsule is pulled in 4 different directions, so this tug of war causes the capsule to be at an equilibrium location between the constraints. Like walking, we first compute the target transform based on the wanted displacement of the player's input. The biggest difference with walking is that we compute the target transform every 0.2 seconds instead of every physics update. This is because it gives us a better idea where we will be in the future, but also provides us more stability with the hands and feet placement. Once we have an idea where we will end up, we need to validate if each constraint's location are still valid with the character's morphology. I will make the right hand as an example, but it's valid for each limb. As you can see, once the right hand reaches an uncomfortable position, we update the location of the constraint. To do that, we scan the environment around the target transform and decide on a new location. If we cannot find a new anchor, the constraint will not update its location. This typically happens because the supporting platform is ending and we cannot go around. This will block or limit the character's movement in some way. Although my example is showing that the constraint moves instantly, we lerp between the old position and the new one over 0.2 seconds to not create instability or abrupt movement on the character. Here, you can see the different tests we perform to decide where we want to put our hands or feet. The capsule is not centered around the character because we are showing where we think the character will be in the future. Like I said before, having 4 constraints means that we can have multiple supporting platforms. If so, it's possible that they move away from each other. This can put the character in a situation where we need to let go some constraints. To deal with this, we continuously monitor each constraint to see if they are compatible with the character morphology and each other. Here, you can see Bryn climbing on one of our epics. Look at her feet. Due to the epic's movement, she's put in a situation that forces her to let go. The constraint breaks due to a combination of her morphology and the shock of the movement. When we need to break some constraints, we will favor the hand and let go the feet first. If we absolutely need to break a hand constraint, we will try to keep the one that was moved the most recently. For constraint setup, it's a lot like when standing still. We want to follow our platform, so we prioritize location. Like walking, it's possible that we are pushed by external forces, but contrary to walking, we want to actively resist being moved by external force. This is why we do not really care about velocity while climbing. There's also a big difference. It's in the way we want hands and feet to interact with the environment. Hands are holding something and they can push or pull. To represent this, we configure the hand constraints to operate in all directions. There are no limitations on the different axes of the constraints. Feet are different as we do not hold onto anything. They can only push. So we want them to detach easily from the surface we are climbing on. Because of that, we only allow the constraint to operate on a plane tangent to the surface normal. As soon as there is any movement in the direction on the surface normal, the constant will not be able to resist and will allow the movement. Let's take a look. This was the goal, and this is what we were building for. Our epics are constantly moving and changing shape. This puts a lot of stress on everything that we built, but it works very well, as you can see. Our character can freely climb on our epic's body. One thing of note here is that our epic's bodies are not kinematic. They are always animated with physical animation. For example, if our characters was in the armpit of an epic, it could be squished between the arm and the chest and pushed inside the epic's body. A game like Shadows of the Colossus avoids this by slow movement and never bringing each body part close enough to create the issue. With physical animation, though, the epic's body will be blocked by the character's capsule, and we can guarantee that, that there's a safe space for the character. With all the physics involved, the resulting movement is often quite not predictable, but we still need to animate our character, so I'll go briefly over our animation flow. Although our movement is handled via physics, the way we animate our character is more traditional. Our biggest difference is how we trigger animations. For example, when the player pushed the left stick on their controller to make the character move forward, the animation state machine will not immediately start to play the walking animation. Instead, the controller will configure the walk constraint and we let the physics engine do its work. Once the character have a non-zero velocity, the animation state machine will start to play the walk animation. If the velocity gets high enough, the animation state machine will decide to play the run animation instead. We also perform full body IK to adjust the hands and feet to fit the ground when or the wall while climbing. In a few states, like climbing, the resulting animation pause is then fed to Unreal's physical animation system to avoid having body parts going through collision. Like a lot of games with combat, we also use root motion, but instead of moving the character directly, we take the root motion information and use it to dynamically configure the character's constraint. This allows animators to give the feel they want for an attack, but still support the physical aspect of our controller and character. Because of our small team, we do not want to create a lot of animation for climbing, and we ended up with a system that is almost entirely procedural. As you can see, without the procedural animation, almost nothing is animated. Basically, only the head move. The arms and legs of our character are entirely animated with full body IK. When we change the location of a climb constraint, we create this spline in space between the previous location and the new one and use it as an IK target over time. I hope this gave you a good overview of our system. One of our key learning is that it's a lot of fun to embrace physics as a gameplay mechanic, and players have an innate understanding on how objects react in the real world, and this translates directly in their understanding of how a character moves in the game. It lets players be imaginative and try to find their own solution to the problems the games creates. We at Yellowbrick learned a lot while making it, and I hope this will help you if you decide to make your own physical character controller. Thank you, and does anybody have questions?